Okay, so let's look at the solutions of the two questions that I gave, special questions for 5.2. And so in both questions, basically, they've asked us to find the diagonal matrix that this A has, if it's diagonalizable, and then find the corresponding matrix P. So how does it work? So remember, step one, we first need to know what the eigenvalues are, so the characteristic equation. And we know by now what we have to do is subtract lambda from the diagonal, and everything else is the same. Now this is an extremely easy determinant to develop because we have several rows and columns with a lot of zeros in. So if I do first, let's say row 3, then I have this 3 minus lambda that I can factor out, and then what's left is 2 minus lambda 0 0, 3 minus lambda, which we immediately see is 3 minus lambda times 2 minus lambda times 3 minus lambda. And again, we see that one factor is there twice, so we get here lambda is 3, kind of twice, but okay, we cannot write that, and lambda is 2. That are the eigenvalues. Okay, step 2. In order for this matrix to be diagonalizable, we need to have 3 eigenvectors that form a basis. And in other words, what can happen? Well, lambda is 2, has only multiplicity 1, so it will have basis 1 single basis element. So that's only going to give us 1. But lambda is 3 appears twice in this equation, and therefore, potentially, it has dimension 2, the eigenspace, and that's what we want. Then we have enough. If it's not, then it will not be diagonalizable. Okay, let's work it out. So let's do the tricky guy first. Lambda is 3. Are we getting what we want? So what we need to fill in is lambda is 3 in this matrix. So what we get is minus 1, 0, negative 2, 0, 0, 0, 0, 0, 0. Now that's very nice, of course, because we're almost done, right? Except for the negative sign, which I'm going to kind of. So row 1, replace that by minus row 1, and I'm going to do this right away here. Okay, I hope that's okay. All right. So sorry, we don't need to do this anymore. Okay. So this is what. Let's analyze this thing. We have a pivot variable that's x1. But that's the only one. So we have 2 free variables, and now we already know the answer. So these are free. What will the dimension be? Then how many basis factors will we have? 2, because we have 2 free variables. Okay, and that's exactly what we wanted, because otherwise we won't have enough. Okay, so quickly can write this down, right? x1, x2, x3. We see that x1 is equal to minus 2 times x3, x2 is just itself, and x3 is just itself. So remember, we have to now split in the parts that have an x2 in it, which is only one of them, and then the one that have an x3 in it, that is minus 2, 0, 1. Of course, when I say only one, that means 0 elsewhere, right? So we have a basis. This is the basis here, consisting of 2 elements, and this will be the 2 elements that we're going to put into our matrix P, right? So sorry, I just want to get this here. Where is this? Okay. And that's for lambda is 3. That was very quickly. So now lambda is 2. What's the eigenspace there? Well, now we do the same thing, but we put lambda equals 2 now, right? Now lambda is going to be 2 here. So what do we get? 0, 0, negative 2, 0, 1, 0, 0, 0, 1. And again, we're almost done. We have to shuffle around a little bit. So I'm going to do some row operations. I'm going to basically, when it comes to shuffling rows, it's sometimes more annoying to write down the row operations than to actually do it. So I'm going to just say I'm doing the row operations that shuffle, and I get 0, 1, 0, 0, 0, 1, and 0, 0, negative 2. Okay, so you can figure out exactly what the row operations are that I did here. Things that are so obvious like this you can do, but any other row operation, or especially if you combine certain things more than just shuffling around, please indicate. Okay. okay, what is missing is, of course, it is not echelon form, right? Because we have this pivot and this pivot, so we have to do one more row operation, namely row 3, replace that with row 3 plus 2 times row 2, and then we are done. We're going to get 0, 1, 0, 0, 0, 1, 0, 0, 0. Great. Let's look at what we have. We have two pivot variables, x2 and x3, and we need to have this, otherwise something was wrong, one free variable. And can never be more than one, because lambda equals 2 was a single solution here. The factor was with multiplicity 1. That's the way that we express this. Okay, so what does this mean? Let's do this in black. x1, x2, x3. Now x1 is the free variable, so it's equal to itself. And we see that both x2 and x3 are equal to 0. So we get x1, 1, 0, 0. And that's the basis for the eigenspace corresponding to lambda is 2. So now step 3, we can form P. Now this answer is not unique, because I have a bit of a choice here which basis vectors I put and in which order. I found with this method, I found these two basis vectors, but you could find different basis vectors if you do things differently. Okay, a basis is not unique. There are many bases. If you think about, we have actually talked about this perhaps, or remind you of it. If you have a basis of vector space and you multiply it with say a basis of two-dimensional vector space, and you can get new bases by having a transformation that has whose determinant, the matrix is a non-zero, is invertible. Anyway, there are many bases. So I'm going to make a choice here, and I'm going to just put this one here and these two guys afterwards. I'm doing that because that's the one that they give in the back of the book as well. But any order in which you write these columns is correct. Okay, so that is P. Now, step 3, what is P inverse? We still have to find the inverse, because the whole form, sorry, P, and I should also write down what D is. Sorry, let me do this first. Remember, D is a diagonal matrix, but again, the way that you build P also determines how you build D, because this was an eigenvector for lambda equals 2, so we get a 2 here on that diagonal element. So we have 3 diagonal elements, right? These two guys have lambda 3, right? Yes, eigenvalue 3, so there will be a 3 and a 3 here, and the rest, of course, it's a diagonal matrix, the rest is 0. So that is D. And then we know that by the theory, we should have that this holds. So this is step 4, perhaps. Let me put it this way. Step 4, verifying. I don't know what it was actually asked, but I'll do it, and I'll probably will ask sometimes. So verify that this is actually correct. And you might say, well, why? We know it's going to be, I might have made a mistake, and then I see the mistake, but why? Well, in today's lecture, you saw that it actually was important that we know what P and P inverse were, both. Okay, so P inverse, how does it work? It's a reminder here of how we find inverses of a matrix. In this case, it's again extremely simple. What we do is we take a matrix and then augment it with the identity matrix. And while we try to make this into an identity matrix, the other side will give us the inverse. Luckily, there's basically only one thing I have to do, right? This is almost the identity matrix, the only operation I have to do. This is already echelon form, it's not reduced because of this -2. So I have to do row 1, I use this pivot. So row 1 plus 2 times row 3. We do this. Now, of course, we do this on the whole matrix, including the augmented part. So 1, 0, 0. We multiply this with 2, right? So we get a 1 here, a 0, and then this 1 times 2 comes a 2 there. And then nothing else has changed, and that's the answer. Okay, so this is now the identity matrix. This is E3, all right? And then therefore this is P inverse. And so now let's verify that we have the purported identity here, right? So we have P inverse 1, 0, 2, 0, 1, 0, 0, 0, 1, times the original matrix A, which was 2, 0, negative 2, 2, 0, negative 2, 0, 3, 0, 0, 0, 3. Let me double check. Yep. And then finally P itself, where P was 1, 0, negative 2, 0, 1, 0, 0, 0, 1. Now, in this product, you cannot work, be careful, you can never work this out right away. You have to do 2 by each, always multiply 2 together, and then multiply again. It doesn't matter where you start, so I've been always working on the back, so let me show you can as well multiply for these two together. And of course, I hope you know still how to multiply matrices, right? So this is, you have to go through this row and this column, okay. So we have a 2 there, then 0 plus 0 plus 0, minus 2 plus 0 plus 6, that's 4. No, that's not right. Yeah, no, okay, no, why is it not right? I don't know why I said that. And then 0, 1, 0, okay, that is 0, 0, 0, 0, 3, 0, sorry, 0, 0, 3, and then 0, right, I got it right. And then the last one, 0 there, that's also 0, and that's 3 there. Okay, now I have to multiply this guy. So I just brought this down, right? I just copied it. And this hopefully is now what I need. So 2, 0, 4 times 1, 0, 0, that is a 2 only there. Then we have a 0. Then we have negative 4 plus 0 plus 4, 0. It has to be a diagonal matrix, so that better be 0. And then 0 times 3, that's a 0. 0 times, that's a 3 plus 0, that's 3. And then we have 0, 0, 0. And we have 0, 0, 0. 0, 0, 0, and 0, 0, 3. And there you are. That is exactly D. Okay, so that's, granted this is perhaps a bit too easy a matrix. I might do a little bit more trickier measure, but I'll try to make it so that the calculations are not blowing up. But you see this kind of questions also with 5.1, kind of lengthy, right? There's quite a lot of things we have to do. Okay, and then number 9, I wrote it down here, was this matrix, and the question was, what about this matrix? Can you diagonalize it, and if so, what does it look like? The way that the question is posed is perhaps, I don't know whether you figured it out, that's what they were asking. I'll make it more clear, okay? I will ask, is this matrix diagonalizable? And if so, give the diagonal matrix, something like that, okay? Now, even saying that it is diagonalizable or not is quite a lot of work. We talked about this, because it involves, let's see what it involves. Step 1. We have to find the characteristic equation. So we need to, because we need the eigenvalues first, so that would be 4 minus lambda, 0, 1, 2, 3 minus lambda, 2, 1, 0, 4 minus lambda. I've said that you could, and I want to do this for once showing this, I'm going to do, you could do row operations again. I could use this 1 to get zeros on there, but I'm going to show you, you don't need to if you don't want to. It's up to you. The bigger the matrix, the more inclined you should be to do this, but okay. So I'm going to do row 3, expanding row 3, because there's at least 1 0 in there. You could have done something else, but I'm doing that. So remember how this is go. You go through this row, taking one element at a time, so we take the 1, and then we look at the cofactor of 1. But you have to also make sure that we have the sign correctly. So let me write here. So that would be a plus, negative plus. So we have a positive sign here, okay? And then, so 1, and then the cofactor, that means we sketch out these two. So there's 0, 1, 3 minus lambda 2, okay? So 0, 1, 3 minus lambda 2, okay? And then we have to do this for every element in the row. The next one is 0. Luckily, that's why we chose that. And then this one, the last element is again with a plus sign, because it alternates the sign. So we have 4 minus lambda. And then what we're left with is 4 minus lambda, 0, 2, 3 minus lambda. And you see, it might sometimes be quicker to do this way. Okay, now, because now we have 2 by 2 matrices, so we have a 1 here. So we have the diagonal element is 0 minus the other guy, that's 3 minus lambda, plus, and now we have 4 minus lambda times the product of the diagonals is 4 minus lambda, 3 minus lambda. Okay. Now, why is this not the great method? Is because now I have to actually expand everything and factor. Okay, that might be a little bit more cumbersome because the factorization is not so obvious now. Whereas if you do the row operation, and then you're going to always have at least a factored form. So it's not the best way to do it, and I want to show you can do it, but this is the part where you get normally stuck. Now, in this particular case, we are lucky because we have, it's a sum, right? But in this sum, we have this factor 3 minus lambda that I can factor out. So I get 3 minus lambda, and what is left then? I get I get here a minus 1 plus 4 minus lambda times 4 minus lambda. Okay, so that is 3 minus lambda, and then I get minus 1. Of course, I said I have to expand this. That is 16 minus 8 lambda plus lambda squared. It's actually a double product formula. And so we get 3 minus lambda, lambda squared, minus 8 lambda plus 15. Okay, so we need two elements that multiply to 15 and add up to 8. Aren't we lucky? That is lambda minus 3 and lambda minus 5. They will do that. Okay, so what we see is, remember now we put this equal to 0. I'll say that this is what the characteristic equation is, right? And so what does it mean? We get lambda is 3. This gives me the same thing, and so lambda is 5. So we see that we have two eigenvalues, one of multiplicity 1. That is not going to be a problem. It's this guy. In order for this matrix to be diagonalizable, we need the eigenspace corresponding to lambda is 3 to have two basis vectors, to have dimension 2. Okay, let's check this. So it's no point in checking lambda is 5. We know it will work, unless we made a mistake, of course. But so, okay, so now in this original matrix, we have to subtract 3 from everything. So, sorry, I have to, let me copy the matrix. 4, 0, 3, 2, 3, 2, 2, 3, 2, 1, 0, 4, 1, 0, 4, and now I'm subtracting 3 from everything, so I'll indicate that, minus 3, minus 3, minus 3, so I get the matrix 1, 0, 3, 2, 0, 2, and 1, 0, 1. Great. I have a 1 pivot, so I'm going to use the row operations, row 2, minus 2 times row 1, and row 3, minus row 1. I get 1, 0, 3. So I'm doing this with negative 2, so I get a 0, 0. Negative 6 plus 2 is negative 4. And there I get negative 2. Sorry, no, I'm multiplying now with negative 1 and subtract, so get a 0, of course. That's what I want, a 0 there, and a negative 2 there. Okay. Okay, that's already taken care of this pivot. Now the next pivot we easily make into 1 to row 2 minus 1/4 row 2. Since I'm at it, I can easily also get rid of the 2 in row 3. Okay, so this gives me 1, 0, 3, 0, 0, 1, 0, 0, 0. Now, I can work further, but it's not necessary. To answer the question, I can already answer the question because I know what my pivots are. It's not reduced form, but I know my pivots. So these are the pivot variables, x1 and x2. These are x3, sorry. These are the pivot variables. So we have one free variable, that is x2. But one free variable means one basis element. That's not enough. So the dimension here, remember this dimension, this is the number of basis elements, the size of a basis, is 1. But we need 2 because the eigenvalue was twice a root of the characteristic equation. Because we need to build a matrix, it has to be a 3 by 3 matrix, so we need 3 vectors. We have only the one vector here, which I have not even worked out what it is, and I didn't even work it out for lambda is 5, but I know at least there's one there. There's going to be only one here. That's not enough. So it's not diagonizable, and that's what the question was trying to ask. Diagonize, and I'm going to stop.